So we're going to solve equations that involve trigonometric expressions, and sometimes end up looking like other equations that we know how to solve. So let me be clear about what I mean. So I want you to think about this old example that we've already discussed. Imagine you had this equation: 3 to the 2x. Oops, sorry, that's a little sloppy. 3 to the 2x minus 6 times 3 to the x equals 7. So when you first look at this and you think about trying to solve, you might try taking the log and so forth, but we've shown this example on another day, and here's really what you want to do with this. First off, you want to think of this expression as 3 to the x quantity squared. And you know that's going to be equal to the thing above it because you multiply exponents when you see them like this. All right, minus 6 times 3 to the x minus 7 equals 0. And then my claim is that this is really a quadratic form equation. Do it. So if you don't see right away that it looks like quadratic, do this. Let y equal 3 to the x. And then this equation becomes y squared minus 6y minus 7 equals 0. Okay? Now, if you do that, now it's factorable. What do you get? Y minus 7, y plus 1. And that's because negative 7 times y is negative 7y. That's positive 1y, which gives you the negative 6y in the middle. The product of negative 7 and 1 is negative 7. So that's great. So now you know that y equals 7 or negative 1. But that's not what we were solving for. We were actually solving for x. So we got to be careful. So we really know that 3 to the x equals 7 or 3 to the x equals negative 1. Now we're just solving these things like we normally would. We would try and take the log of both sides or something like that. Here you're going to have x log 3 equals the log of 7, or x equals the log of 7 over the log of 3. You can take a change of base formula. That's log base 3 of 7. Over here, if you just look carefully at it, you realize there isn't any power I could put on 3 to get any kind of negative number. Right? We know 3 to the 0 is 1. 3 to any negative power is just 1 over 3 to that power. So we would never even get a negative number from the left-hand side of this equation. So this thing has no answer, so we'll just reject that. And your only answer is this. Okay. So the idea here was that you could take equations that don't look like quadratic equations and make them look like quadratic equations. So now we're going to do the same thing, except for an equation that involves some expressions from trigonometry. So consider this problem for a minute. Suppose you have this equation. Let's go with secant squared secant squared x plus tangent x equals 3. Okay? And we're going to solve this where x is in the interval 0 to 2 pi. Okay? So we're going to give an answer back in radians. All right. So ideally, I'd like this to look like our quadratic equation. All right. So it kind of looks like one. You see something squared and something and so forth, but there's a couple of problems. So let's take a look at this for a minute. Suppose I do minus 3 equals 0. The problem we have is that this expression and this expression are not of the same form, so to speak. They're not both the same variable. So here's what I'm telling you. This is tangent x in it in the middle. This is secant squared x. If it's going to be quadratic, we would expect these two trig functions to match, and it doesn't. It does. All right. So ideally, what I'd like to do is start thinking about identities that I know that involve secant squared and tangent. Okay. So here's one that comes to mind that doesn't involve those things. It's called the Pythagorean identity. But we know we can go through this thing and divide it all by cosine squared. If we do that, this becomes 1 plus tangent squared x equals secant squared. Okay. So that turns out to be really handy. So now what I can do is solve this problem where I have two different trig functions in the same equation. I'd like them to both be tangent, and that's what I'm going to do by making a substitution. So this equation is going to become 1 plus tangent squared x plus tangent x minus 3 equals 0. And we're okay now. And the reason we're okay is because now it looks more like a quadratic. Just one more thing. Tangent squared x plus tangent x minus 2 equals 0. And sure enough, it looks like a quadratic. Okay. Now if you want, you can start off by saying let y or some other variable you like equal tangent x. And we do that, we get y squared plus y minus 2 equals 0. And you should try and factor that. I think it does, right? You get y plus 2, y minus 1. That'll do it, because negative 1 times 2 right here gives you negative 2, but they add to the positive 1 that you wanted in the middle. All right, so now you know y equals negative 2 or y equals 1. Or we can say it this way. Tangent x equals negative 2, or tangent x equals 1. So now we're in a slightly different place than the problem before. We had 3dx equals 7. Because here now I'm saying, all right, tangent of some angle is supposed to be 1. Okay? So you might remember from knowing your special values, x could be the angle pi over 4. Pi over 4 radians or 45 degrees. Okay? Now, that's not the only angle between 0 and 2 pi that's going to work. Because if we draw pi over 4, here it is. It's in the first quadrant. And there's all different ways to remember things, but tangent is not only positive in the first quadrant. Tangent is positive first quadrant, but it's also positive in the third. So what we're going to do is we're going to redraw that angle over here. Here's the reference angle, the same thing, pi over 4. And we have to ask ourselves, what angle is that? Okay? So to get from the positive x-axis all the way around to this ray here, we'd have to do pi plus pi over 4. Okay? So those are just in case. That's going to be 5 pi over 4. So that's another answer. So far we have answers of pi over 4 and 5 pi over 4. The next thing we're going to deal with is that tangent x equals negative 2. Now, it is not a well-known thing what angle whose tangent would give you negative 2. So you're going to have to resort to your calculator to do that. So we go to our calculator, and we're going to do the following. If you look above the tangent key, there's a button that says like tangent to the negative 1 power. That means tangent inverse. Okay? And then we type negative 2 in. Now, you should be careful about what mode you might be in. This problem did ask us to do everything in radians. So I'm going to check the mode on my calculator to make sure that I'm in that mode. If I press mode, sure enough, there I am. I'm in radian. On a T89, you can see it down on the bottom of the screen. It says RAD. If not, press mode and make sure you're in radian mode. Second quit. So here's where things are a little different. If you're comfortable with angles and degrees, you might not like this. But for now, we have to write the answer, negative 1.107 radians. That's what x equals. Negative 1.107 radians. This whole problem's in radians. Okay. Now, we know that this negative number cannot be between 0 and positive 2 pi. So we're going to have to convert this. So that's what we're going to do. So here we go. Here's our axes. Now this is where I'm convinced that some of us might not be that comfortable. We're all pretty good at knowing, hey, that's 0 degrees, that's 90 degrees, that's 180, that's 270. And then I think you're pretty good at this too. 0 radians, pi over 2 radians, pi radians. This is 3 pi over 2 radians, and now we're back at 2 pi over here. What you might not know is the decimals that go along with these things. So for example, pi over 2 is about 1.57 radians. And pi, you know, is 3.14 radians. Okay, 3 pi over 2, if you type that in your calculator, you get about 4.7. And 2 pi is about 6.28. Okay, So if we're looking for an angle of negative 1.107 radians, then we know we have to head in that direction because negative angles rotate clockwise. And we also know that if we got ourselves all the way over to here, that would be negative 1.57 radians, which is too far. So the angle negative 1.107 radians might be right in there, negative 1.017 or 107. So the angle we really want is that angle. So to get that, what we would do is we would do 2 pi minus 1.107, and that would give us the angle. That's the answer. So let's do that. 2 pi minus the answer. Well, we're not going to do that. We'll do 2 pi plus the answer because it's negative. Enter and enter. So we get out 5.176. So that's our first answer. X equals 5.176 radians. And we got to go do a little bit of thinking again. Because we knew in this case that tangent x was equal to negative 2. Well, there's another quadrant I can be in. Tangent is negative in quadrant 2 also. So while we had this angle of negative 1.107, we also could go into this quadrant with the same reference angle, 1.107. And the angle we really want is that one. So we just do pi minus 1.107. Get an answer for that. Second pi minus 1.107 gives us 2.035. It looks like 2.035. Well, now the question is where to finish the problem. You actually have 4 answers. You have those 2, and then the others that you had, which was pi over 4, and then also 5 pi over 4. Which, if you wanted to, you could write those as decimals. Say this. So here's some handy values of angles that you should know. So, for example, I guess we'll call this column theta, or this row theta. This is going to be sine of theta, cosine of theta, and tangent of theta. So here's some handy values for you to know. All right. So I'll write it in degrees, but you could certainly write these in radians too. Here you go. We showed it earlier how we could get this, but the sine of 30 is 1/2. The sine of 45 is rad 2 over 2, and the sine of 60 is rad 3 over 2. Now, what's sort of fun is cosine, the co means complementary. So the cosine of 30 is the same as the sine of 60, because 30 and 60 add to 90. So this is rad 3 over 2. Okay? Cosine of 45, same thing as the sine of 45. So the rad 2 over 2. And then lastly, the cosine of 60 is the same as the sine of 30, which is 1/2. So some people memorize this like you start off with sine, it's 1/2, rad 2 over 2, rad 3 over 2, and then cosine's the same numbers counting down. Okay? Tangent, we showed in class that that's really sine of theta over cosine of theta. So all we have to do is divide the first row by the second. So if I do 1/2, if I do this fraction divided by that fraction, I'll get 1 over rad 3 because the 2's will cancel. If you want, you could rewrite that as rad 3 over 3 by rationalizing the denominator. Okay? Here you have the same thing divided by itself, so you get just 1. That's why the tangent of 45 degrees or the tangent of pi over 4 is 1. And then lastly here, rad 3 when you divide them. Yeah, talk to you about. So, if you notice, to do these problems correctly, you kind of have to decide what's positive in what quadrant. So some of you remember things like this. All students take calculus, and all meant literally all functions are positive. So all functions are positive here. This meant that the sine was positive and the cosine and the tangent were negative. This meant that the tangent was positive and then the sine and the cosine were negative. And this over here meant that the cosine was positive, but the tangent and the sine were negative. Okay? Now you should know why this is true. And again, it goes back to the unit circle. Unit circle should be becoming your best friend. Okay, so here it is. Here's your x and y axis. There's a unit circle. We showed why the point x comma y can be written as cosine theta sine of theta. Okay, so let's think about that for a minute. So if you look at that red angle I just drew, that red angle is less than 90 degrees. We'll deal with degrees for now. Okay? So if you think about it, any angle between 0 and 90 would land along this arc of the circle. Well, anywhere along that arc in the circle, the x value and the y value would be positive because we're in the first quadrant. So we know over here, x is greater than 0 and y is greater than 0. But we also know that x is equal to cosine theta and y is equal to sine theta. So we can rewrite these as the cosine of theta is greater than 0 and the sine of theta is greater than 0. So that's why everything's positive in the first quadrant. Now, if you're worried about tangent, remember tangent theta is sine theta over cosine of theta. Well, a positive divided by a positive is a positive. So these are all positive in the first quadrant. Now let's go over the second quadrant for a minute and give this a little thought. So now we're talking about angles like this. And in the second quadrant, what do we know? We know x is negative now, but y is still positive. Well, if x is negative, that means that the cosine of theta is negative. And if y is positive, that means the sine of theta is positive. And here's the fun part. Tangent theta would, again, it would be sine divided by cosine, but a positive divided by a negative is a negative. So when we put this s here, we're saying only sine's positive, but now we know why. It just comes from the x and y values. Okay, let's go to the next quadrant. Down here, here's an angle like this, theta, that lands in this quadrant. Well, what do you know? You know that x is less than 0 and y is less than 0. They're both negative. Well, that's the same thing as saying that the cosine of theta is less than 0 and the sine of theta is less than 0. But what about tangent now, right? Tangent theta would be sine theta over cosine theta, but a negative divided by a negative is positive. And that's why we put a t over here in that little mnemonic device, whatever you want to call it. Okay? And now, predictably, the last quadrant, here we go. X becomes positive again, but y is negative. That means that the cosine of theta is positive, but the sine of theta is negative. And then the tangent, which is sine over cosine, would be a negative divided by a positive, which makes it negative. And that's why we put a cosine or a c in the last quadrant, because cosine is the only thing that comes back positive. Those facts are very important in determining the answers to trig equations, because when you write trig equation answers, most of the time when you have an equation like this, like tangent x equals 1, we'll discover one angle right away. We usually have to go to another quadrant looking for a second angle. Okay? So you might remember all students take calculus as a way to figure out where to go, but now you kind of know where it comes from. It comes from this pretty picture here.